Hello everyone, Professor Dustin here, and in this video I'm going to introduce Coulombs Law. So Coulombs Law is the law which helps us model the electromagnetic interaction. So first let's think about some of the other interactions we have already studied this year in physics. One important example was the gravitational interaction. So remember, gravitational interaction is a long-range interaction. Two objects can be separated from each other and experience a law of gravity. We also have studied a number of contact interactions. That includes things like the normal force, frictional force, really all the other forces that we've been dealing with. And remember that these interactions are short range. So what's interesting about these examples is the gravitational interaction. That's a fundamental interaction in physics. Everywhere in the universe there are gravitational forces and they all act in exactly the same way. What's unusual about the contact interactions we've studied so far, the normal force and the friction, they're not fundamental. They only exist because there are objects there for us to push on to exert normal forces on us, or objects which create friction. It turns out that all the forces in this category, in our real life, normal forces, friction forces, other pushing forces, these are actually electromagnetic interactions. They're not fundamental interactions like the gravitational force. They're interactions which exist because it is electromagnetism which holds objects together. So let me try to give you an example. So here's a model for essentially the old story of me pushing on the wall and the wall pushes back. This large object over here, that is going to be the wall, and this is going to be a model for my hand. Okay, it really looks like a piston or something, but it's going to represent my hand. So what's happening when my hand pushes this way on the wall? My hand is made up of a bunch of little tiny molecules, like hand molecules. Okay, it's really, the molecules of my body, basically of my skin and my muscles and all those kind of things. Those molecules are all being held together by electronic forces because there are various kinds of charges, protons, and electrons in there that are forming molecular bonds. Those objects are all being held together by the electromagnetic force. In the same way, the wall molecules, which is actually wood or concrete and paint or whatever, are also being held together by the same electromagnetic forces. So the actual reason why my hand doesn't go just straight through the wall is because there's actually a repulsive force between these guys that's preventing my hand from going through the wall. Now this is an exceptionally complicated issue, what's going on with how these things are all attached, what's going on with how these things are attached, and how the repulsive force works. That's all very complicated. We are only going to be dealing with interactions between single particles, not between a mess of particles making up an object, because that's a much more complicated issue. That's essentially material science. And we only want to deal with what happens between individual single particles. Well, it turns out that writing down the force between two charged particles is actually quite simple. So now I'm going to blow up just these little guys here into a picture. So there are my two charged particles. They're going to be separated by some distance. I'm going to call that R. And I'm going to give each of them a charge. I'm going to give the first one a charge Q1 and the second one a charge Q2. So these charges could be positive or negative, and you've probably already learned that charges that are the same, meaning positive positive or negative negative, they will repel each other, whereas charges that are opposite, positive negative, will attract each other. Well, now writing down the force, which describes this interaction, is actually very simple. I'm going to start by just writing down the magnitude of that force. So I'm going to call this FQ. Some people like to call it FC for the Coulomb force. I'm going to call it FQ because it's the force between two charged particles. It's just going to be equal to K, which is going to be a constant I'll discuss. And then the magnitude of Q1 times Q2 divided by R squared, where R squared is the distance between the centers of the two particles. So a couple important things to notice here. The first most important thing probably has to do with this magnitude sign here. So what I want to write down the magnitude of the force. Okay, well I have an R squared on the bottom. R is a distance, so even if this was a vector, okay, it could have negative components, but R squared is definitely a distance and R squared is definitely a positive number. K is going to be a positive number. Q1 and Q2 could be positive or negative. So if I'm not careful with these absolute value signs, then my magnitude could come out to be negative. To make sure that doesn't happen, I'm just going to say, okay, no matter if Q2 and Q1 are positive or negative, just take absolute value of both of them to be sure that this FQ is always going to be positive. So when we're going to have to deal with the direction in a moment, but for the moment, we can forget about the direction and just say this product is a positive number. Okay, so I should say something about this K. It's called Coulomb's constant, and it's named after Charles Coulomb, who discovered this effect in the 18th century, and it has a specific value. 8.988 times 10 to the 9th Newton meters squared per Coulomb squared. Typically, you'll see this number approximated as 9 times 10 to the 9th for many calculations because 8.988 is so close to 9. So we can check the units of this expression pretty easily. We want the answer to be in newtons. There's our newtons. Q1 and Q2 are charges. They're going to be in coulombs, so K times 2 charges will cancel out the C squared on the bottom. This will be in meters, meters squared. It will cancel out that meter squared, and we will end up with force in newtons, as we expect. So that constant serves to basically convert the units of this part of the expression into the correct units for the force, and is just something that you have to know or know where to look up and find. I would also like to mention that there's another form of the Coulomb's constant. People often write K as 1 over 4 pi epsilon naught. So that's the same value for K, but epsilon naught is a different constant, which is 8.854 times 10 to the minus 12th. You can express Coulomb's law in either fashion, either with K in right there, with this constant, or with just K. I will mostly use just K because the expression looks a little bit simpler than to have these extra symbols in there. So what about the direction of Coulomb's law? Well, we know that we can put in the direction of this force. If we wanted to write this force as a vector FQ, we could do that because we know that the force is either attractive or repulsive based on the signs of the charges. So it turns out it's actually quite easy to write this explicitly as a vector expression. I just need to add in the displacement vector between the two charges, and I'm going to do that by just writing this as our vector. So that's just the displacement between the center of the two particles represented as a vector going from the first one to the second one. And then I'm also going to use a unit vector. So a unit vector, which is going to be in the same direction as this r, but only one unit in length, and I'm going to call that r hat. So that's in the same direction as r, but it has a hat over it. So that's the direction vector corresponding to the displacement vector, but it has length of 1, and now it's very simple to write an expression for Coulomb's law in a vector form. Do that over here. FQ as a vector is simply the same thing as I have over there without the magnitudes now, because if these charges are opposite in sign, I want to actually get the repulsive or the attractiveness of the force based on their actual signs, and then I can just write r hat like that. So this makes this a real vector equation because the force is directed along the line between the two charges with the direction given by the direction of r hat and the sign of Q1 or Q2. Q1 and Q2, if they are the same size, this is positive, and that means the direction of the repulsive force from Q1 and Q2 is going in that direction, meaning bigger r, so that's repulsive. If they're opposite signs, that means that the direction force of Q1 and Q2 is towards Q1 because you get a minus sign here and you get in the opposite direction of the r hat vector. So obviously the next thing to do is a practice with this force, trying to calculate the size of this force based on some set of charges or a configuration of charges, try to figure out the magnitudes and try to figure out the directions. It turns out, as you can probably expect, the magnitude is pretty simple to figure out, but the direction in a full vector sense can be more complicated, especially when there are a number of charges around. Okay, great. Thanks very much. This has been an introduction to Coulomb's law. Thank you very much for watching.